Okay, this is probability part 2. We are going to do some review, but I like these notes because they kind of have everything in one spot. Please follow along. So single probability and independent probabilities of compound events. First off, probability is the number of successes over the number of possible outcomes. So, for example, if you consider getting ahead a success because you called ahead, well, the probability of that happening is 1 out of 2 because you want ahead out of the 2 possible outcomes. Okay, probability of A and B if they are independent. Okay, remember and just means multiply. So if I said, what is the probability of flipping a coin and rolling a die? And I wanted to get ahead, that's my success, and I also said I would get a 5. Well, there's a 1 in 2 chance of getting ahead, and a 1 in 6 chance of getting a 5, so if you times them together, there's a 1 in 12 chance. You can see the visual representation in the notes part 1. Let's look at an example. Just like we did with set theory and logic, we can make a Venn diagram. And in this case, we have a box of 12 count Crayola crayons. And in there we have yellow, blue, red, white, green, violet, turquoise, brown, peach, black, magenta, and orange. And we want to find the probability of reaching in without looking, because it has to be random, and managing to grab a peach. Well, there is only one peach crayon out of 12, so that's very easy. What about the colors in the American flag? Well, those would be these colors. There are 3 of them out of 12 crayons, or 1/4, or 25%. I could then say getting a primary flag and an American flag and a primary color. Well, primary colors are yellow, blue, and red. American flag colors obviously are blue, red, and white. And so if we look, how many colors are both? 2 out of 12, or 1/6 chance. And then the probability of getting a pink crayon, well, this box does not have pink, so in this case it's 0%. Okay, examples of joint probability. Notice here that it said and, but it was only one crayon. So it had 2 characteristics. It was primary color and American color, but it was only one crayon. Here now for joint probability, it could be 2 crayons. That's the difference. Okay. Blindly picking one crayon, noting its color, then putting it back and blindly picking another crayon. Okay. Putting the crayon back, just like we talked about, is an example of with replacement and keeps the probability independent because it returns the box to the original state before you pick another crayon, just like I showed you with the sticks on the previous video. The probability can be found using the joint probability of independent formula, which is that. Okay? So, for example, probability of getting an American flag color and a primary flag color. So, we always think about it as reaching in, picking a color, putting it back, reaching in and picking another color. In this case, you can't reach both hands in at the same time, or it wouldn't be independent. And I shouldn't say both hands at the same time. I should say you can't reach in with one hand and pick 2 crayons out at the same time. That would be without replacement. You have to put it in, get your crayon, record the color, put the crayon back in the box, and then reach in and pick out another one. Okay? So, probability of getting a flag color, again, there are 3 flag colors, so 3 out of 12, or 1/4. There are also 3 primary colors. If you multiply them together and simplify, you get 1/16. This may also be shown to you in a contingency table, or otherwise known as a frequency table. And this frequency table below shows the results of a survey of students regarding their chores and curfew. So if we want to look how many students were surveyed, well, there were 18 kids with chores, 15 kids without, so a total of 33. How many kids have chores? Well, 18 out of 33. The probability that a kid doesn't have a curfew, go this direction, that's 8 out of 33. Okay, and these are called marginal probabilities because they're found using the margins of this table. If we have some compound probabilities, now we're going to use the inner part of the table. So, has a curfew and has chores. Well, yes, they have chores. Yes, they have a curfew. That is 13 out of all 33 kids. Has chores and doesn't have a curfew. Chores but no curfew. 5 out of 33. And has a curfew. Okay, in this case, how many kids have a curfew? Total, 25 out of 33. So this one is also marginal. Notice that these two are not, and that's because they were compound. They had and, or they could have also said or. Okay. Another joint probability example would be find the probability of randomly picking two students and getting one who has chores and a curfew, then returning to the group and picking one with no curfew. So this is before they were individual probabilities, but we were having two things happening. One kid, okay, so this was one kid, both things. So it was individual. Well, now another joint, okay, two kids. So curfew and chores, and then no curfew. So a curfew and chores, we already decided from up here, was 13 out of 33, and I'm going to go ahead and erase some of this other coloring so you can see. And then we put that kid back, so we still have 33 kids to choose from. And then what's the probability of getting a kid with no curfew? Well, a kid with no curfew, that is 8 out of 33, or this part. And then because we want them to both happen, that is an and. We'd multiply them together and we get 104 out of 1089. Okay, for the next page, we're going to talk about this independent formula again, and we're going to use it in a different way. We're going to prove something being independent or not. Okay, so what we have is the number of 10th, 11th, and 12th graders, and then their gender. And it says, are being a male and being in 10th grade independent? So they're going to be independent if the probability of being a male, and let's go ahead and use, let's be sexist and use blue for male. The probability of being a male times the probability of being in 10th grade, if that's the same thing as the probability of male and being in 10th grade. And this we can find from the table as well. If we didn't have the table to find this separately, then we would just have to assume that they were independent. But let's see, probability of being a male. Well, there are 832 males out of the total number of kids, 1571. 10th graders, there are 605 kids out of 1571. So those are marginal probabilities. And then it says male and a 10th grader. Now we'll look in the middle. Okay, it's compound. Male and 10th grader, there are 320 out of this. So let's go ahead and multiply the blue and the green and see if they equal the orange. And it turns out they do, which means there's no relationship. You're not more likely to be in the 10th grade given that you're a dude. So they are independent. Let's go ahead now and look at it from the female point of view. We're curious to see if the probability of being a female and being in the 12th grade is independent. Well, let's think about a real-world situation where maybe it wouldn't be. Maybe the 12th grade program at Hillcrest has our robotics program is trying to cater to girls. And so we're drawing girls in just like we do with the IB program. So we have more 12th grade girls than we do boys they're coming to this fancy robotics program. Okay, that would mean that they were independent, that they were not independent. There's some relationship between being a girl and being in the 12th grade at this school. So again, just like we did before, we would go ahead and look at them and say, okay, probability of being a girl, 739 out of the total. Probability of being in 12th grade, 413 out of the total. Multiply those together and we get 0.129. But if you look in the middle, the probability of being a female in the 12th grade is only 216 out of the total. These do not match, okay? So there is some type of relationship here between being a girl and being in the 12th grade at this school. So they are not independent. All right, vocab again. Events are dependent if the occurrence of one changes the probability of another event occurring. For example, drawing marbles from a bag with replacement is independent, while drawing marbles from a bag without replacement is dependent. Notice I've now defined this like 5 times. It's because you have to know. A probability that takes into account a given is called a conditional probability. So we're going to use this idea to build a new probability type, which is called conditional, and you will have to memorize the formula I'm about to show you. Well, hopefully it's in your formula packet, but you'll have to memorize how to use it. A given condition, and I'm going to make it green because this shows up so much it's important, it's like money. A given condition is when we already know the outcome of the events. For example, when flipping a coin and rolling a die, the probability of rolling a 6 given heads means we already know the coin has resulted in heads. This is written as 6 given heads. So we rolled a coin, we got heads. Now what's the probability of getting a 6? Well, that's still 1 out of 6. So these things are independent. Nothing changes. So here's my definition for that. Events A and B are independent if and only if they satisfy the probability of A given B equals the probability of A, or the probability of B given A equals the probability of B. The question is what? This is the deal. If we know B happened, we still have the probability of getting A. It's exactly the same. So probability of getting a 6 was 1 out of 6. There's 1 6 out of the numbers 1, 2, 3, 4, 5, 6. That didn't change once I found out I had a head. Or vice versa, if I knew I got a 6, that's not going to change my probability of getting a head. It's still 1 out of 2. So this is another definition of independence using conditional probabilities. Knowing one is not going to change the probability of another happening. Okay, so this is what they might ask you. If the probability of A is 0.7 and the probability of B is 0.3 and the probability of A and B are 0.21, are A and B independent? Well, they are independent if the probability of A times the probability of B equals the probability of A and B. So let's check. 0.7 times 0.3, that's 0.21. Oh, yep. They are independent. Okay. Now we have dependent and conditional probability.